So, right, left node, right traversal of a tree. This is called in order. The three traversals we usually have are LNR, NLR, or LRN. It's named for where the N comes. If the N's in the middle, that's in order. If the N comes first, that's called pre-order. Right, the N comes before everything else. If it's LRN, that's called post-order. So, in order, LNR of T, base case, if your tree is null, just return. Otherwise, do the following three things. Do an LNR traversal on the left subtree. Print the data in the root, and then do an LNR traversal on the right subtree. That's all you gotta code. Base case to get you out of the recursion. Otherwise, it's two recursive calls to the same function with a print somewhere in the middle. If you want to do pre-order, again, if T is null, just return. Otherwise, do the pre-order on the left subtree. Do a pre-order on the right subtree. Print the root data beforehand.
And the post order would be after.
Post order would be called LRN on the left, LRN on the right, and then print the data. After. Mm-hmm.
That's interesting. The N actually kind of determines what the function is.
Yeah, it does, exactly. So one of my suggestions for PA4 is make yourself a small data file. Right, so here I have a database. My first license plate is 20, and the name is just root. And license plate 10, the name is left, and 35, the name is right. What's going to happen when I run that through PA4 is my 20 comes in first, that's going to be the root. And then I'm going to read a plate that's equal to 10, that's going to come on the left. And then I'm going to read this plate 35, which is alphabetically after 20, that's going to come on the right. So if my PA4 is working correctly and I feed it this database, this should be the tree that gets built in the mind of the computer. And now when I say star dump, I should get the different traversal orders of this. So, so the height is going to be 1, because it's one hop to the deepest nodes. This will be balanced. We'll talk about balance in a little bit. But let's look at the traversals. The in-order traversal should give you your data in alphabetical order. So this should give me 10, 20, and 30. The pre-order is going to give me the root node first, and then the left subtree, and then the right. And the post-order, LRN, is going to give me the left subtree, the right subtree, and then the root. So you can check your code up to that point. If you've got your code, reading in a database by using a database file like this. Or you can just use the sample program and feed it your own database. Right, so there's our tree. The height is 1. It is balanced. The in-order traversal is 10, 20, 35 as we expected. NLR is 20, 10, 35. Right, and the last one, LRN, should be 10, 35, 20. Right, which was the order it traversed them in. So you can play around with your understanding of traversal order and trees and how these things get built up by using plate 4 and just feed it your own databases. Yeah?
Is it correct to say that the main function for this assignment is almost the same as the last assignment?
Yep. Yeah, you can reuse most of your main program from PA3 for PA4. The commands are slightly different. There's no load command. But you know, same thing. You initialize a structure, you open up your database file. Your command line processing is the same, except there's no second argument. It always has to be run with exactly one argument, which is a database file. You open that database file, make sure that you can open it, read in your lines, parse them into a plate, first name, last name, and then you're going to call your trees add routine instead of your hash add routine. That gets your whole tree set up, and then if they say star dump, you're going to call a bunch of functions that will give you information about the tree. Otherwise, take what they type in as a plate name and call your search function. If they say star delete, do the delete once we talk about delete. All right, so backing up, I finished grading PA3. I posted comments and grades on that. PA3 looked really good, okay? Memory leaks are always a challenge, but most people manage to avoid memory leaks, and most people even manage to avoid the warnings that you get from Valgrind when things aren't initialized, which is awesome. General comment on Valgrind issues: they're easier to find as you develop your code, right? So if you've just finished your add function, right, and it looks like it's working, run Valgrind on it. Because if you're getting a memory leak and you weren't getting it before, you know it's something related to your add function. As opposed to, you know, finishing the whole program and then you run Valgrind for the first time, and if you've got leaks, you've got no way of knowing where they are, and you have to start doing some sleuthing. So if you keep the memory leaks down and keep those uninitialized warnings down from the start, that's a little less work later on. So I feel like people are doing really well with hashes, definitely with lists, right, as far as understanding the concepts. Difficulties with the main program, that's just something to keep working through, right, and come and talk to me if you want. There's still some people who are doing way too much work. They're getting a character, they're checking its ASCII code, and if it's a digit, they're doing an ASCII to I and all this kind of stuff. scanf will do all that work for you. Okay, you want to know if someone said star dump followed by an integer, just scanf star dump space %d. If it returns a 1, you've got it. It was a star dump followed by an integer, and scanf has already given you the value of that integer in a variable, right? Otherwise, you know, you string compare, etc., etc. So don't make extra work for yourself. We won't use globals for the rest of this stuff, so the issues people ran into with globals, don't worry about those too much, but come and talk to me if you didn't figure it out. But that's probably the only time we'll have to use globals for anything in this course sequence. So yeah, things look good. If you've got questions about it, or you've got some part that you couldn't figure out, or you want to talk about your feedback or whatever, just come and talk to me, or shoot me a note, and we can go over it. But I think people are in good shape. PA4 is a variation on PA3, different data structure, but you can reuse a lot of the code. And then PA5 will be a group project most likely. It will probably be related to something called dynamic programming, which will be basically heavy recursion. So the recursive stuff we're developing and working with trees will all come into play for the final programming assignment. And so my general loose plan is to spend this week talking about trees, hopefully get up through tree deletion in the next day or two. And then I want to talk about balancing trees. And I didn't ask you to balance your trees for PA4, and I don't want you to balance your trees for PA4 because it will register as not doing the right thing. But I want to talk about balance algorithms, and we'll talk about balance today and why balance is important. We'll talk about something called an AVL tree, which is a way to have trees that stay balanced. I want to talk about other ways to traverse trees, in particular something called breadth-first search, which will bring us back to finally talking about queues. And so trees will probably finish up, this week, maybe part of next week. Next week is week 8. So, after this week, we got 3 weeks left, 8, 9, and 10. So we'll finish talking about trees, we'll talk about queues, and then I want to start talking about dynamic programming, okay, which is basically breaking problems into subproblems, which is the essence of recursion. We'll work with a bunch of interesting problems in dynamic programming. I want to spend some time talking about sorting and searching, things beyond a bubble sort. Look at different ways to sort data. So we'll spend probably a good part of a week doing that. I want to talk about graphs, which are kind of like trees, but more general. We'll talk about some graph algorithms, particularly something called Dijkstra's algorithm, which is a way to find the shortest path from one point to another in a connected graph. So you're trying to travel from one point to another, and you know how long it takes to get to each point in between. What's the optimal route you should take to minimize your travel time? And there's a famous algorithm for solving that called Dijkstra's algorithm. And that's probably going to take us through the end of the course. So it's coming quickly. But let's work on trees this week, okay? So we've talked about height, right? Height is the distance from the root to a node. Tells you the height. So tree depth tells you the distance to a particular node. So the root has a depth of 0. Everything one level down has a depth of 1. And depth is really just sort of how far you are from the root. So if we go from the root to this node down here, we have to follow 1, 2, 3, 4 steps. So if you draw your tree nicely, right, everything at this level will have the same depth. All of those have the same depth, all of those have the same depth, and so on. Okay, the height is the depth of the deepest node, so the height of this tree is 4. And we observed that you could find the height of a tree recursively by looking at the left subtree and looking at the right subtree. And whichever one is got the greater height, the height of that tree is 1 less than the height of the original tree. Because the distance to get from this root to any node, well, you have to add 1 more hop if you start at the original root. And the same thing over here. So we had this recursive algorithm we could use, which basically said the height of a tree is either 1 plus the tallest height of a subtree, right? The height of the left subtree or the height of the right subtree. Take the largest of those, add 1. That gives you the height of the original tree. Except if your tree is null. If your tree is null, there is no left or right subtree, so this will blow up. So we put a special case. If the tree is null, height's -1. Okay? Really straightforward, totally clean, recursive function that describes the height of a tree. And we can code that in C by just writing a height function that calls itself. And that's totally legal. Okay, so you got an idea of height, right? It's sort of intuitive. It's how tall the tree is, basically. What's less intuitive is this notion of balance. So balance, the basic idea of balance is we want our trees to be filled in from top to bottom as wide as possible, as full as possible before we start going deeper. So suppose I want to put 7 pieces of data in a tree, right? Here's a really nice way to do it. Right? My total tree has a height of 2. It's not very tall. There's no way I could put any more data in here without making the tree taller. I've used every possible spot. Okay? Here's a tree that's slightly less ideal. right? Why is it slightly less ideal? Because this node down here is deeper than all the others. And I could have put it, you know, right here and kept the tree a little shorter. Instead, I put it down and made the tree deeper than I necessarily had to. That's not quite as well balanced as this original tree. Same with that. Even more so with this. Even more so with this. Way more so with this. And even worse with that. Okay? So balance is not so much, you know, how many things are on the left and how many things are on the right, even though it looks like that. Balance is really about trying to fill things in at each level before you go deeper. So this might be balanced in a physics sense. Right, I have 9 nodes here, and yeah, I got the same number of stuff on the left as I do on the right. But if I were to fill things in as I went down this tree, right, I could fit those same 9 nodes in the tree like this. This has a height of 3, this has a height of 4. Right, and I'm not taking advantage of all these other spots in here that I could have been putting things in, and so on. So that's the sort of intuition behind balance. We want it to be fluffy and not too tall. Okay, so here's a definition of balance, and this is the definition we're going to use. Okay, so a tree T is balanced if and only if one of the following 2 things is true. Possibility 1, the tree is empty. An empty tree will be considered balanced. Okay, that's just an edge case. It's easy. If the tree is null, just say, yeah, it's balanced. Okay, the other possibility is all 3 of these conditions have to be satisfied. The 3 conditions are as follows. The tree's left subtree has to be balanced. The right subtree has to be balanced, and the left and right subtrees have to have approximately the same height. More accurately, they have to have heights that differ by no more than 1. So the absolute value of the difference in heights is less than or equal to 1. If all 3 of those are true, the tree is balanced. Otherwise, it's not. And you've got to check all 3 of these things. No 1 or 2 of them alone is sufficient. And that always gets people on tests and programming assignments. You got to do all 3. So let's look at some of this. Suppose your tree is null. Is it balanced? Okay. And what is its height? -1, that's just a definition, edge case. Okay, suppose your tree consists of a single node. Is that balanced? So see if all 3 conditions are satisfied. So what's the left subtree of this? It's null. What's the right subtree? Null. A null tree is balanced, a null tree is balanced, so conditions 1 and 2 are true. A null tree has height -1. Since the left and right children are both null, the left and right children both have a height of -1. Those are within 1 of each other, right? -1 minus -1 is 0, so this is balanced. And I'll just note here, this thing has a height of 0. Okay, what about this tree? So it's not null, so we got to satisfy all 3 conditions. So what do you think? Is this balanced or not? I mean, it doesn't look particularly balanced, but it should be. So what's the left subtree of this?
It has a height of 1.
So this tree has a height of 1, right?
The right side has a height of 0.
So let's be careful. This whole tree has a height of 1 because the deepest node is this one and has a depth of 1. The left subtree of this is what? It's just a node with no children. What's the height of this tree? That's a height of 0. The right subtree is null. What's the height of a null tree? -1. So 0 minus -1, that's 1. That's less than or equal to 1. So the heights differ by no more than 1. So we've satisfied condition 3. Is the left subtree balanced? Right? We already decided a thing with a single node is balanced. And the right subtree is null. That's balanced too. All 3 conditions are satisfied. So yes, this is balanced. And if we make a really pretty tree like this, that's definitely going to be balanced. The left and right subtrees both have height 0, and the left and right subtrees are just single nodes, which are balanced. All right, what about this? Who thinks it's balanced? Who thinks it's unbalanced? So let's look at the third condition. What's the left subtree? Left subtree looks like this. What's the height of that? 1. Okay, the right subtree looks like this. What's the height of that? 0. So 1 and 0 differ by 1. That's legal. Okay, so condition 3 is fine. Condition 1, the left subtree has to be balanced. Well, that's the left subtree. Is that a balanced tree? All right, we already did the recursion for that, so we already found that's balanced. The right subtree is a single node. Is that balanced? So that actually satisfies all 3 conditions. And so even though it looks sort of lopsided, that's balanced. What about that one? That's going to be balanced too, exactly the same thing. The left and right subtrees each have height 1, and the left and right subtrees both look like this. They're balanced. So this is balanced. But if I add an extra node off of here, this will be unbalanced. Why is that? Well, let me do a different case first. Let's look at this. So is this tree balanced? Right? So the left subtree is this, that's balanced. The right subtree is null, that's balanced. But if you look at the height of the left subtree is 1. The height of the right subtree is -1. 1 and -1 differ by 2. That's too much of a difference. This is not balanced. So now if we ask about this tree, which has 3 nodes hanging to the left, what's the left subtree of the root? These 3 nodes hang in a line. That's not balanced. We can stop right there. And we can say this is not balanced. So intuition doesn't always work for this, but we don't need any intuition at all to code this up. To code a balance function, we do the following. If the argument is null, return true. It's balanced. Otherwise, call the balance function on t left. If it's not balanced, return false. We're done. If it is balanced, call the balance function on t right. If it returns false, return false. We're done. It's not balanced. But if this also returned true, saying the right was balanced, now call our height function on the left and the right. Calculate their difference, see if it's between 1 and -1. And if it is, we can say, yes, the whole tree is balanced. If this is bigger than 2, we can say, no, it's not balanced. Okay, make absolutely sure you do all 3 of these. Don't just do these or don't just do that. It's got to be all 3. So it's a recursive thing. So questions about that? Recursion is a theme. Everything we do from here on out, including some of our sorts. We're going to keep thinking recursively and working with this. And it's a powerful way to program. You can fall into a mindset where you start seeing everything as recursive. And we don't necessarily want everything to be done recursively, but you can.
Because I think it goes endlessly with these issues.
It was what?
It goes endlessly with these issues.
Yeah.
But then it starts really
Yeah. So if you recurse too deeply, you start to get into potential memory problems. But let's say my job is to count whiteboard markers, right? So I'm moonlighting for Scott or something. And he'll hand me a bunch of markers and say, tell me how many markers are in your hand, right? Well, I can count them, you know, the normal way, but I want to practice my recursion. Okay, so I'll look at my hand. If my hand's empty, I'll just turn around and I'll say 0. That's easy, right? Otherwise, I have at least one marker in my hand. Here's what I do. I take one marker out, I hand these to a friend, and I say, tell me how many markers you have in your hand. And they'll say 4. I add 1 to 4, I say 5, that's the answer I give back. And I never have to do any work, right? I have to know if my hand's empty, well that's easy. Otherwise, I take out one marker, I ask somebody to count these, and I just add 1 to their answer. It's a nice recursive way to count markers, right? And then the recursion part is that, you know, my friend is myself. So I have to count these while I put them down and I leave and come back, and it's like, oh, I need to count these markers, you know, and I do the same thing. And that'll work. That'll actually give you a count. So that mindset is a powerful one. Yeah, but if it's really yourself, you can just keep talking to yourself until you lose track of where you are, which is when your stack has run out of memory. So here's some linked list code that I've written. And I just wrote the add part and the print part. Okay, so add will add numbers to my linked list, and print will print the contents of the list. And I got rid of my sentinel node here. So my empty list is null. And if I have something in my list, that first thing in my list is not a sentinel, it's actually the first piece of data in my list. So I don't need an init list anymore. I initialize my list by just setting it equal to null. And my add function, right, I take the value that it returns and I set list equal to that. So here I'm just adding a bunch of numbers into my list, and I'm adding them in a weird order, right, 10, 5, 20, 40, and so on. And then I'm going to print my list. And if I run this, right, it'll print my numbers in sorted order. So I'm inserting into the correct spot in the list. But I'm doing it recursively. So how do I add to my list? Well, if my list is null, it's an empty list, I make a new node and I just return that. Okay, that's a base case. That's just saying, you know, there's nothing in the list. Okay, I'll make one node. Here you go. Here's your list. Okay. Otherwise, if there is stuff in the list, I just check to see, should I insert at the beginning of the list? Is the number I'm trying to insert smaller than the first node's value? And if it is, I make a new node. I point to what was at the beginning of the list, and I just return my new node as the start of the list. So that's inserting at the beginning. That's always easy, right? Otherwise, I need to find the right spot in the list to insert. I don't want to do previous, current, next, do a loop while this is not equal to null and have seg false and all that kind of stuff. So how do I do this? It's one line of code. I use this handy function called add. I give it everything after the first node, and I say insert my number into that list. And then I have my first node point to whatever that new list is, and I'm done. So if someone hands me a list and says insert a number, if it goes right in the beginning, I just put it in the beginning and point to the old list. Otherwise, I take the first thing out of the list, so there's a shorter list, and I hand that to my friend and I say, can you insert my number into this list? They hand me back the new list and I make my first node point to it, and I'm done. And this totally works. And the print function is even more fun. How do you print a list recursively? Well, you know the first thing you got to do is print the first node's data. Well, first of all, if the list is empty, you don't do anything. Just print a new line because there's nothing to print. Otherwise, print out the first node's data and then print everything else that's in the list. So just pass lists, whatever list is pointing to, whatever that first node is pointing to, the remainder of the list, pass that to your print function, and you're done. No loops, no whiles, no segfaults. Okay, that's a recursive version of a list print. So there's times where it might be easier to write a recursive solution, but it's not a better solution. Okay, recursion takes memory. If my list was 10,000 elements long, I would be calling myself 10,000 times before my list ends up being null and I start doing my returns. I might run out of memory if I do that. Right? So this would not be a general solution I would want to use. But to play with recursion and think about, you know, how things can be defined recursively, this is a fun exercise. And we can do the same thing with delete. How do you delete from a list? Well, if the first node is the thing you want to delete, just get rid of it, free it, and return the address of the next node. Otherwise, delete it from the remainder of the list. So take the rest of the list, pass it to your delete function, and let somebody else deal with deleting it. All right, so this is how we traverse trees. We use recursion, and recursion is definitely the best way to do tree traversal. We can do it without, but the problem with traversal is you got to keep track of stuff. So let's say I want to traverse this in left node right in order. The very nature of this is recursive. This is really saying, to traverse this tree, first traverse the left subtree, then print the root node data, then traverse the right subtree. Okay, that's a recursive definition inherently. You have to work to make it non-recursive. To traverse the tree, first traverse the left subtree, then print the root node, that's the end, then traverse the right subtree. If you want to do node left right on this original tree, that means first print the root node data, then traverse the left subtree, and then traverse the right subtree. And if you try to do that without recursion, it's really confusing. So this basically means go as far to the left as you can, print that, pop up one level, print the root, now go to the right, and you know, if there's something else over here, don't print this 15 just because it's on the right, go as far to the left as possible, and then pop up here and print the root node, and then try going to the right, and then pop back up here, and come over here, and you know, here's a 15.5, so when you come here, don't print the 16, see if you can go to the left. Right, and then print the root and come back here. And now pop all the way back up here, and now pop up here and print the root data, and now start doing the whole thing on the right. It's really twisty-tangly to try to do it in your head, unless you have lots of fingers to sort of keep track of where you need to go back to. But it's 4 lines of code, right, if you write it recursively. So how do we do LNR traversal on a tree? Do LNR on the left subtree, print the root node's data, and then do LNR on the right subtree. That's the essence of it. The one small detail is you need to make sure that your tree is not null, because if your tree is null, any of these are going to cause a seg fault. So if t is null, just return. And so change print to printf and put parentheses around t is null, and replace is with equals, and you've got C code. For node left right, move this print statement up here. Print the root data, then traverse the left, then traverse the right. So node left right of t. If t is null, return. Otherwise, print the data from the root, and then do node left right on t left, and then do node left right on t right. And left right node, same thing. Do left right node on left right node on right, and then print the root data. So once you have a tree, right, which you can cobble together by hand, you can start coding these and running them and see if what you're getting makes sense. And a handy base case is just a 3-node tree. In order should be in increasing order. NLR, which we call pre-order, should print the root node first, and then the left, and then the right. And pre-order, or post-order, left-right node should print the left node first, and then the right node, and then the root. And if you can build this tree in memory and get those 3 traversals right, you're probably in good shape. Everything else should happen automatically, but you can try bigger trees and see if it's making sense. The in order, left node right, you can always tell if that's right because things should be alphabetized or in numeric order if you're doing a tree of numbers. Yeah, check the paper and you know, once you have an intuition that you traverse a 3-node tree LRN by going left, right node, now if you wanted to do a tree where, you know, you had something up here, well, you know you're going to do, so let's think about left, right node. You know you're going to traverse this in left, right node, which should give you 10, 30, 20. And then you're going to traverse this left, right node, which should give you 45, 60, 50. And then you're going to do the root node 40. So make yourself some cases, right? And this is more good stuff to work on with friends, right? Make some sample trees and run your code on it and draw some sketches and talk about it and decide what the order should be and so on and so forth, right? I don't want you comparing code, but working on this stuff, trying to understand the concepts, playing with test cases, stuff like that, right? That's all a good opportunity to work with other people and kick around ideas and so on and so forth. So you're welcome to do that. And it's good Discord stuff too. All right, so let's talk about insertion. So doing a tree of integers here. So T is the root node of a tree. It's a struct node star. It could be null if the tree is empty. And again, all of our tree functions that can change the tree are going to want to return a pointer to the root. And when you call this, you're going to say something like root equals add parentheses root comma data. Okay, because we don't have sentinels here, so sometimes we need to change the thing that we're pointing to. And we can't change this argument, right? So we can return the value of the new root, the pointer to the new root, and then set our root equal to that. So how do we add to a tree? Well, there's an edge case. Which is if our tree is null to begin with, let's just make a new node containing our data and return that as the root of the new tree. Okay, otherwise, and I don't need to say else here because if this condition is true, I'm going to return. So I've got a built-in else, which is if I come to this next statement, I know that I'm in an else condition, but I'm not going to say else. Every time I say else, I get more indented. It's more housekeeping. So if T is null, just make a new node and return it. Otherwise, we want to insert into either the left or right subtree. Right, so this is our intuition. Here's our original tree. And I want to insert a 12. Well, I'm going to look at my root node, which is 20. 12 is smaller than 20, so I have to insert somewhere to the left, which means I'm going to insert somewhere into this tree. So I'm going to call insert on this tree and say insert a 12 into here, and then whatever it returns, I'll just have 20 point to that on the left. So I'm going to basically say insert into this tree the number 12. And it will return a tree that looks like this. And then I'll set 20 to point to that. And so my new tree looks like, 20, 40, 30 on the right, 20 points to 10, points to 5, 15, but I got a new node hanging off the 15, which is a 12. The reason I need to change my root node's left to point to the new root is the following. Suppose I insert a 12 into this tree. Okay, I'm going to say 12 is smaller than 20, so I'm going to insert into the left subtree. I'm going to say insert into null a node containing a 12. And this is going to return a tree with a single node whose root value is equal to 12. What I need to do is take 20's left child and have it point to that. So now 20 has a 12 on the left, and then it's got the usual stuff on the right that it already had. So I got to do two things. So if my data is smaller than the root data, and can this ever segfault? Anytime you see an arrow or a pointer dereferencing, you should wonder if it's going to segfault. It can't. The only way it would segfault is if T is null, and I've already checked to make sure T is not null. Okay. If T is some crazy value, it could segfault, but assuming it's not, we only got to worry about the case where it's null. Okay, so if the data is smaller than the root value, we want to insert it into the left subtree. Well, how do we do that? We say add T arrow left, comma data. And then we need to make sure that T arrow left points to that node. right? Else, do it on the right instead. And then return T, the original root. Okay, that's a perfectly working tree insert function. So base case, if the tree is null, just make a new node and return it. Otherwise, call your add function on either the left or the right subtree and return the original root. Yeah?
Are we going to a case where the data is equal?
We're not going to worry about the data being equal,
Okay.
so we can assume it's always different. So if you're in doubt, you could call search before you allow add to run.
Sure.
This is going to add equal things to the right, it looks like. But that's going to make other things confusing, so we won't worry about equals. All right, does this make some sense? So, make your tree by hand in memory by piecing nodes together. Get your traversal functions working, or at least one of your traversal functions. And then try to get your add function going. And if you have a tree that you're starting with, you can just call add. With something like, root equals add root comma 42. That should add a 42 to your tree. If you want, you can start off with root equals null. Alright, you can add a bunch of things and then call your traversal code. And it should show your data in increasing order. Looks a lot like this. Why? Because lists and trees are similar in some ways. They're structures to which I can add things, I can delete things, I can search for things, I can print the things that I've stored. This could be code that I'm using for a tree, except I'm using the word list for a variable instead of root or tree. But, and print could be a traversal function that I have for my tree. And this main program will work fine. When we get to Java, we'll deal with things like collections. We won't even know how those are being implemented. They might be linked lists, they might be trees, they might be something else. Right? We're not going to know, we're not necessarily going to care. So, go for your add function. Once you've got that working, search is easy compared to add, and then there's delete. Okay, so we're working our way up to delete. Probably tomorrow we'll start talking about delete. But definitely if you have questions on any of this stuff from PA4, let's talk about it sooner rather than later. All right, I will see you tomorrow.
You said we're doing delete tomorrow?
I think we'll start it tomorrow, yeah. I think we're just